Okay, I think we'll start.
Yes, sir.
So, welcome everybody. Thanks for joining this 6th ISAMP web colloquium. And today we have Professor Harshvardhan Wanare from IIT Kanpur. It is my great pleasure to introduce Professor Wanare. He is associated with the Department of Physics as well as Center for Lasers and Photonics at IIT Kanpur. He received his PhD from University of Hyderabad in 1998, after which he worked at Washington State University and Illinois State University in the United States as a postdoctoral fellow, and later joined IIT Kanpur in 2000. Professor Wanare is a theoretician interested in various aspects of light-matter interaction, including coherent control, quantum optics, metamaterials, photonics, among others. And although a theoretician by training, he has strong collaborations with the experimental groups. He is also an excellent teacher and frequently dwells in the development of pedagogy. Apart from research and teaching, his academic interests extend to exploring application of optical techniques in development of biomedical diagnostics. And with this, I invite Professor Wanare for the talk.
Yeah, thank you, Aditya, for giving me this opportunity to share some of this recent work that we have done. And these are tough times, so thanks for everybody for having been able to make it to this talk. All right, so I have been told that many of the participants are students, and I was told that more than 50% would be students. So I will keep this at a very elementary level. So from the experts, I would seek apology before I even begin. This is the title of the talk, Taming of Superpositions through a Weak Perturbation. And almost everything that I have written down on the first slide is probably familiar to you. In some context or other, we have seen superpositions, perturbations, weak perturbations, control, and notions like that. So let me tell you a small story and then begin the talk. Right? So the context is what I want to start with, something very elementary. And we are going to look at all these aspects, not particularly this system, but a system which is almost can be sort of mapped on to such a simple system. So the idea is on the left of your screen, you would see that there is a double well kind of a potential where the two wells are reasonably well separated. So you see that once they are reasonably well separated, there is little torque between the two wells. And if you calculate, now these are identical wells, so the energies are exactly the same. So the blue line and the orange line actually show you the energy which is identical for both the wells. And now if you look at the corresponding ground state wave functions, you will see that, one of them has got a peak. The left one is lying well within the left. There is hardly any extension of that left wave function into the right one. And similarly for the particle in the right. So you see now one can do, so these are now degenerate. So what you will see here is the word degenerate energy states. They are equal and there are two of them which are of equal energy. Now as you decrease the separation between the two wells, so please look at the figure on the right, and now you will see that something else has happened. So once these wave functions start overlapping significantly, then you see that what you get is some kind of a coupling between the two wells. The extent of coupling is given by the lifting of degeneracy. So you see that the energy which was just E now has become E1 and E2. And you see this delta E, which is the difference between the two, gives you the extent of coupling between the two wells. Not just that, the form of the wave functions have themselves dramatically changed. So now what you have is a sort of superposition of something that was localized in the well 1 and 2. The superposition is such that one of them is an even function and other one is an odd function. This is a 1D problem. So you see that one does get kind of a superposition which are known as psi plus and psi minus. Psi plus correspond to the lower state, the ground state, the symmetric one, and for the higher state it becomes that. So you see now you suddenly get two orthogonal states right? These are now orthogonal states, which are non-degenerate because of this introduction of this coupling between the two wells. So this is a problem that one is very familiar with and looks at it in various contexts, from chemistry to elementary quantum mechanics and so on. So given this, I'm going to talk about a variety of little terms, and I just want to state them. These are just thrown on the slide just to distract you, basically. So I'm going to look at eigenstates or modes of a system. I'm going to look at perturbation. I'm going to focus a little bit on symmetry and breaking of the symmetry. So symmetry breaking is going to be important. Then we look at orthogonal states, lifting of degeneracy. See, all these terms we have just spoken of in the previous slide. Then we are talking about linear superposition. And all this game is going to be played in a playground which is called the photonic crystals. So photonic crystals gives us a very nice, happily engineerable field in which you can try out many of these simple ideas. And these are actually used in devices today, given the tremendous amount of optical communication that you have. Photonic crystals are at the heart of it. Right, so we will look at photonic crystals, cavities formed in them, waveguides, something called defect states, coupling, and all this is going to be put together to talk of a sort of a new control modality. Actually, the ideas are not new at all, just that they are talked of in a sort of newish context, right? So you will agree with me as I go along, right? So let me just first begin with introduce to you what is photonic crystals. So again, with apologies to the experts. So you see, just like we have crystals, the normal crystals that we talk about for electrons inside a material. So you see, what you have in a crystal is a periodic arrangement of atoms. And this periodic arrangement, what happens is now the electron, which is, think of it as a probe particle, sees this very periodic potential or a periodic interaction. And because of this periodic interaction, what happens is really that you get, because of this interaction between the nearest neighbor and the periodicity, what you get is bands. That is, you have electrons that can have energies within the allowed bands, and no energies are possible, or are the electrons with energies in between in the band gaps, or rather between the bands is not allowed. So what you get is basically a notion of band. Now you do a similar thing for optics. Now, of course, to keep in mind is that the scales have changed. For when you look at a periodic arrangement of atoms in a normal crystal that we talk about, typically the scales are of that of, at the most angstroms or tens of angstroms, but and you're now looking at electrons in that kind of a matrix. Whereas when you look at optical light, optical radiation, then you are suddenly talking of a wavelength which is 500 nanometers. So obviously you require periodic structures of that length scale. So typically what you do is you arrange materials of different refractive index, okay, which tells you the amount of sort of the interaction, if you like, which is a measure of the interaction of the probe with the system. So probe here being light and the system being the material itself. So you arrange this material in a periodic fashion, and again, lo and behold, exactly the same physics. What you get is sort of a bands, allowed bands, and band gaps. Now, of course, you can make these arrangements in 1D, you can make them in 2D, you can make it in 3D, and that's a kind of depiction that I'm showing here. And each one, of course, comes with its own nice properties, its own nice applications, as well as its own complexity. So, which we will not so much worry about, but I can tell you that for my talk here today, we are going to largely focus on something called a two-dimensional photonic crystal. Right. So, two-dimensional photonic crystal, how do we think about it? So one can think of it as periodic arrangement of rods, right? So these are rods in air. The rods could have finite refractive index, and the gaps between them is all air. So again, you have a periodic arrangement. You see that along the vertical horizontal direction, there is no periodicity. So that is why, whereas in the plane of this, Okay, in the plane, you would see that which is perpendicular to the screen. You see that there is actually a periodic arrangement both in X and Y. And if you like, the Z axis is the one which is perpendicular to it. So you have a two-dimensional periodicity, or you could do the other way around, which is to take a slab of material and drill holes in it, right? So either of these are done depending on ease of making and so on. So there are fabrication challenges in each and every kind with a lot of detail. Okay, so for example, these 1D things are basically layered media stacked together to create a photonic band gap, an allowed band, and so on and so forth. And imagine this periodicity is broken, then one will start seeing something called a defect state. So I'll come to that a little later. Similarly, the 2D as well as 3D. Imagine this. This 3D is actually very popular, where you very difficult to obtain optically for optical wavelengths. But it is basically a pile of wood, if you like, arranged in this fashion, right? So, but fabrication is completely different. Absolutely exciting story. The people who do fabrication know it all. They have to worry about multiple things, multiple material properties, their responses. Things in the bulk don't behave like things when you're looking at films, and then so all kinds of complexities come in, and I will simply not go in that direction. So being a theoretician, I can take that liberty and basically talk about something that we know, right? So I'm just showing you a picture. This is not necessarily from this. I picked up from the internet or somebody else's work. So basically, what you have on the left-hand side is now a periodic arrangement of holes, right, made inside gallium arsenide. And you see, and you left out a few holes to be made at the center. So you see, this becomes like a defect, wherein, if I just remove even one hole, that will become a point defect. And this kind of this kind of region starts behaving like an optical cavity. That is, if I put in light for which the rest of the structure is such that that the light falls in the band gap, that is, it is not allowed to propagate in this structure surrounding it. So if I could put in that light at the center into this cavity, it will basically retain there. And that is what a cavity is. Practically, when you put two mirrors and you confine light within, here what you have got is a series of holes which is confining light within this small region. Now these regions can be extremely small, because you see you are looking at a sub-micron scale, and the quality factor, which tells you the extent to which, once you put in the light, for how long will it last in this cavity without really leaking out into the surroundings, it can be pretty high. So that is measured by something called a quality factor or a Q factor, and people get about a million these days quite easily, and 10,000, 100,000 is easily got. Now you can see clearly why this is now offers us exciting possibilities. I can probably create two cavities and couple them. I can probably have it's kind of close to ours, but what you have done is removed a series of rods here to make a waveguide, then removed a series of rods here. This behaves like a, think of it as a cavity, or you can think of it as a circular resonator, okay, where left circle you are going along clockwise or anti-clockwise directions, and then you have another waveguide. So you can come in with light at the terminal A, at the port A, if you like, and then you can get out at B, C, or D. And just by playing around with this central structure, which is a waveguide sort of, or a cavity coupled to waveguide and so on, one can adjust variety of parameters and basically get very, very interesting flow of light within such structures. For example, one can actually now close off this the channel B and channel C, and that will act like a reflector, where you get light coming in, circulating here, and appropriate amounts going out. So these are kind of things which are done, which is done for the sake of technology, in terms of getting the photons into the right channel at the right place, and so on and so forth. So this is widely used in optical communication, and these small structures actually form the heart of these the information processing, because it allows coupling between various channels and very smartly puts in light from one to another, depending on, so you can think of wavelength multiplexing, depending on the wavelength you will be put to various channels and so on and so forth. So I just want to get into that regime and talk more about it, but let's just get to other ideas which are relevant for my talk. So the next important idea which I want to talk about is symmetry. So you see that we already had a symmetric arrangement of atoms, a symmetric arrangement of, in this case, rods or holes. So on your right, I have now this a little cluttered transparency, cluttered view graph. Please bear with me. So what you have is basically series of rods, and I'm looking at it from the top view, and this is the cross section of it. And you see that these series of rods are actually arranged in a square lattice, right? So the distance between them in both the X and Y direction is exactly the same. And this is what is precisely my photonic crystal. But I've done a little bit more. What I've done is I've taken this central rod and increased its size, right? So you see, just like when we stopped in the other view graph, I showed you that we did not have, we had a few missing holes. What you have done here is by creating a larger rod, one has actually created a defect. Just like the defect in that case, this is also a defect. Now you see, if you look at this defect as your central pinning region, now this forms like a cavity. So your field will get localized around this if I come in with the field which is within the band gap of such a photonic crystal. Right. So you see now, now let's look at the symmetry of the problem. Now you see, if I take this structure and if I rotate it by 90 degrees, I will come back to exactly the same structure. So this is what is called as a C4 rotation. Okay, because I can divide 360 by 4 and that I get 90. So that's why it's called a C4 rotation. And I'll get back to myself. Now there are other symmetries which are there. You can think of 4 different planes. One is the plane along X, where there is a reflection symmetry between the top and the bottom. And then there's a plane along Y, that is a horizontal and vertical planes we talked about. And there is a plane at, there may plus 45, and there's a plane at minus 45, which is also the plane of symmetry. So you see that I can take reflections across these 4 planes and get back my same structure. So you see that such a symmetry, this point group symmetries are studied very well and actually exploited very well by chemists. We will not get there, but this is called a C4b symmetry. For these reasons as I mentioned. Right. So now, what do we do with this symmetry? So what one can do is look at the Maxwell's equation, which is the wave equation, and then look at these operators corresponding to these symmetries. For example, so my H is now the operator that governs the wave equation. You will quickly recognize there's a del cross kind of a term, with 1 over epsilon being the, in here epsilon is now the periodic permittivity, dielectric permittivity of the medium. And you see one gets a Hamiltonian here, there's an eigen equation, eigenvalue equation, and one can now look at the commutation relations of this Hamiltonian with such a structure. So the previous structure I showed you, indeed, what do you mean by commutation? If it commutes, implies that these 2 operators, the sequence with which I operate them doesn't really matter, or rather, both the operators can have simultaneous eigenvalues. There are multiple ways of looking at the same thing, but basically the rotation with 90 degrees, the reflection across x-axis, y-axis, plus 45, minus 45, all these are operators that commute with this Hamiltonian in this square. I'm now talking about this the square lattice which I described earlier, and this basically tells you that if you have such a system with such a symmetry, there will be doubly degenerate dipole modes which are permitted for such a system. So that is something that is governed by symmetry, right? Now what I want to do is, I want to do a little bit more, and just kindly look at the right hand side, which is what my system I showed you. But now I want to look at this symmetry and break it ever so slightly. So you will see that there is a little dot which is there beside the central rod. Remember, the central rod was acting like a cavity. And then I have put another very small rod just beside that, And you see clearly, if I put in such a rod at an arbitrary location within this central cavity, you see that this is going to break the symmetry, right? So this is not a mistake. It is just that it's a very small rod. And this is what I'm calling it as a small perturbation to my cavity, which is there, right? So this is what I'm going to look at and see what this little perturbation does to my system. All right. So this is just the more magnified picture of it. So I'm indicating this little dot as a rod, which is of a very much smaller radii than the rods that constituted either the photonic crystal or the cavity, which is a central rod, and so on. So what happens is, as I told you, you get doubly degenerate states, both in terms of eigenvalue. They are degenerate in the sense they are same eigenvalue. You have two states without this rod, right? But once you put in this rod, you break symmetry. So what happens is that these two states, so I'm showing now the band diagram. This yellow region shows these are energies. So on the left, I'm plotting energy or frequency. On the right, I'm plotting the k vector or the direction of propagation within such a crystal. And then you see that the energy is no longer degenerate. The degeneracy between the two states is lifted. So this amount of lifting has got to do with this properties of this little rod. And I will tell you ahead that it's got to do with the optical depth of this little rod. So what matters is basically its area times the refractive index or the permittivity of that rod. So I will come back to that later. But essentially what you get is, because of the presence of this defect, what you have is now two non-degenerate states which are there, right? And both of these are dipole modes and they are non-degenerate. So these are some parameters. I don't know why I put it here, but it will probably not make any sense because it is Greek symbols and almost Latin and Greek. But so epsilon here is the permittivity of the rod. R is the radii of the rod that you have. A is called the lattice constant. That is, every rod in that arrangement is separated by a distance A. Either I will use 1 micron or 0.5 micron. And then the central rod is RC. Its radius is 0.33A, which you see is larger than the rods which are otherwise aligned. There was 0.2A. And the perturbation rod is 1 order of magnitude smaller than that. So it's really, really small. So we are in this regime, which is basically that the perturbation rod is smaller than the central rod, and both of these are actually smaller than the wavelength, right? And similarly, I will not only concern myself with square lattice, I will also look at hexagonal lattice. The parameters are different. And then we also look at, in hexagonal lattice, we look at a hexapole mode, just like a dipole mode, and that has different parameters. So this just so that if somebody asks me a question, I can tell you what exactly the values were. Right. So now this is something that happens. So mode rotation was the word, and I want to get to that. So please look at the right hand side, and again my view graphs are quite cluttered, so please bear with me. So you see, these are the two without the perturbation, that is without that little rod. These are the two dipole modes which are supported by in that cavity region, okay, within this cavity. So you see that these are aligned along the x-axis, red being positive, blue being negative, just the indication. And then you have the central null region, this is like a dipole. And similarly, a dipole mode which is allowed along the y-axis, aligned along that direction. So you see, these are the two directions in which naturally the two modes are aligned. And these are at the moment degenerate. Now what I do is, please come to your left. But now what I do is I look at a small perturbation at 45 degrees, that is between the x and the y-axis. So this little is basically like a enhanced view graph, enhanced part of that. Think of it like a small lens. You can see this little rod beside the larger rod. And now something dramatic happens. So the mode is no longer aligned along x and y. The mode actually gets aligned along the 45 degree direction. Not just that, this mode is different from the other mode, and so there were two modes. One mode gets aligned, the other mode becomes orthogonal to this mode, right? This is orthogonal to the location at which the rod is placed. You can clearly see now these are perpendicular to each other. Now, does it really work only for 45 degrees, or can I come in with an arbitrary angle? So the amazing thing is that if I come in at 75 degrees, exactly the same thing happens. The mode aligns along the 75-degree direction, and you have an orthogonal mode which is perpendicular to that. Now, see, these are non-degenerate, and I can tell you that for every arbitrary, angular location of this little rod, one will actually start rotating this dipole mode as one places the rod along. Not just that, you get two modes. One is a mode which is along the direction of the rod, other one is perpendicular. This has got an energy which is lower, this has got an energy which is higher. That is the non-degenerate two states, and that is what happens in presence of this little perturbation. Right, so now we can do actually something better. So indeed, just like the original old case of the double well potential, let us try and write down the new state which is generated, psi1 and psi2, in terms of the old states x and y. Remember, x and y are the unperturbed states, they degenerate. And now I'm writing down basically superpositions. These are like alpha and beta, which I indicated in my in that first view graph. But you see, you can basically write this down. And my student, Gagandeep Kaur, who is probably in the audience, she's the one who did this immense, fantastic job of figuring out what are these factors that govern the superpositions. Now, I'll just tell you quickly, this phi1 and phi2 take a value of plus minus pi. That depends on, once you fix the rod, these values are fixed. And they basically depend on how far away you are from the band edge. So you go from plus minus. So there is just, basically these gives you plus minus signs. And once you have fixed the rod, they remain as it is, right? And now you can take the rod and rotate it. That is, if you have fixed the optical density of the rod, this phi1 and phi2 will remain the same. And now you see that this theta parallel is basically the orientation angle of the rod makes with respect to the symmetry cavity axis, right? So there is a theta parallel, which is telling you the theta, and the one which is the second state, which is perpendicular to that, it is basically pi plus minus pi by 2, depending on whether theta is positive or negative. So you see that this is now the complete form of the superposition that is generated by introducing this little rod at a location theta within the cavity. Now you see, this is very useful because once we know that these are the weight factors of these, one can actually manipulate these weight factors to do something more, right? So what we do is we will try to do something more, which is to couple these cavity to waveguides. So again, my view graphs are getting more and more cluttered, more and more information. So what I have is the original cavity, the original structure. But now what I did is to remove a series of rods along the X and the Y direction. But I use these directions because I want to retain the symmetry of the system. The original C4b symmetry of the system without this perturbation rod needs to be retained. So I remove this. So now you can clearly see light would come in from the left. For example, in this waveguide, the structure is much larger than what I've indicated here. This is just a cartoon of the central region of interest. So a light can come in from the left. It can go into these three different ports. So now it's a 4-port input-output device. I can put the light in from wherever I like. Not just that, I can take the light out from wherever I like. And again, what I do is I put my little perturbation rod and see whether I can control the flow of light in such a system, right? This is a reasonable question to ask. And particularly because we have now some kind of a hold over the superposition state that governs this flow of light, can one actually do better? And can one actually control? And that is the question that hopefully the answer would be yes. Right. So now, the poor Gagandeep had to work even harder, and she actually figured out what is the superposition of the states that we now couple to. This is the state, the psi1 and psi2 are the new states which are there. But now you don't merely have something which was, like what you saw earlier. There is also these are not basically terms with magnitude unity, but these have got some phase factor, some amplitude factors as well. These A1x, A1y, A2x, A2y, these are all real numbers varying from 0 to 1, right? So let me just first clarify that. And then what you have is, you of course have something like this. So please look at this, for example, this factor. There is n here, which stands for, the n stands for the number I have given to these various ports. So port 1, I have called it n equal to 0. Port 2 is n equal to 2, n equal to 1. N equal to 2 is port 3. N equal to 4 is, n equal to 3 is port 4. Okay, so 0, 1, 2, 3 instead of 1, 2, 3, 4. Right. So what you have now is, if I come in with light from the first port from the left, that means my n is 0. So then this will become theta 0. As simple as that. If I come in with a light which is, so that is this theta 0, I will measure from the direction of the propagation of the light. So let's say if I'm coming in from the x-axis or going along in the horizontal direction. So let me switch on my laser pointer. If I'm going along in the horizontal direction, then along the horizontal direction, my x-axis, and because I'm coming at n equal to 0, I will start measuring my angle from the x-axis. If I'm coming it along the y-axis towards the bottom, I'm going from top to down, I will start measuring the angle from the y-axis, right, from that axis. So that is why these angles depend on in the source with which, in the direction in which the source is putting in light. All right, so these are of course familiar with what we did, but now let's look at these pre-factors which are there. Now these pre-factors very nicely separate out. So this was surprising to us, but it made sense. So you have some factor that depends only on theta, and some factor that depends on the choice of the rod. So once you have chosen the rod, these factors get fixed, whereas the theta dependence can now be chosen around by turning around the rod location, and then you can go around. That is controlled by this, and that is simply basically the cosine. Is basically the projection of that. So that is the kind of term that we get in A1 and A2, which governs these prefactors. Now please look at the right hand side. So you see that the psi1 state is the one I told you, it's aligned along the rod. I have made the rod a little darker just so that it's visible, and the orthogonal state is perpendicular to that rod, right? So these are psi1 and psi2. Now if you look at this psi1 state, there is a little, so when we did this calculation, we always had this little mismatch varying from about 3 to 4% in our calculation. We were wondering how to fix it. And we realized quickly that you see the overlap of the field along this little rod is more for this state in comparison to this state. This state, there is a zero field here, there is very little overlap. So this basically gives you symmetric transmissions if you don't do anything else along the plus and minus y direction, whereas this gives you something different along different directions depending on this overlap. So there is an asymmetry factor which we pin down, and this asymmetry factor, basically we have shown that it is related to the electromagnetic energy density difference between these two modes. So that is just some detail, but we are worried. We have managed to fix that number. So now that you have something like this, now let us see what the outputs are. So what I'm doing here is I'm coming in with light from the left, and I'm looking at its transmission in the port 2, 3, and 4, right? So all my angles are theta 0 now. Theta 0 parallel and theta 0 perpendicular, because I came in from the port 1, which is n equal to 0. So you see that if I'm coming in 1 and I look at the transmission in 2, this is how at theta equal to 45 degrees, I get, this is the transmission. In the port 2, in the port 3, this is the transmission, and in port 4, that is the transmission, and rest of the right is basically reflected out. If I change my angles, you see that if from theta equal to 45, I'll realign this this little rod at 75-degree angle, and I will get another set of transmission. You can clearly see that these transmissions in various ports are controllable, right? And they start, not just that, the width of this transmission basically depends on how isolated this cavity is. So for example, I remove 4 of these extra rods. So you see that this becomes sort of a leaky cavity, and now the transmission broadens. So you see, I can either have a narrow band filter or a wide band filter. That is, light within this narrow band or a wide band will be transmitted depending on what I do with this little rod, which I have kept there. Either I move it away, move it around. So there are various ways of controlling the widths, either by changing the perturbation rod or by changing the cavity characteristic itself, and so on and so forth. So one can actually achieve these narrow and wide band filters where one can steer light into various ports, right? Now, do we have to do a lot of calculations? No, because we have already figured out what the governing factors were for the superposition. One can simply write down whatever they were, okay, calculate them, write it down once, and then you can get basically transmissions the way you like. Just take the mod square of the amplitude factor, and that is the amount of energy that is going to be put from one channel to another. So that becomes very straightforward, and it basically, so we have done multiple calculations with variety of parameters, and this basically beautifully captures all the other idiosyncrasies that the system will have. It basically follows the superposition state that we are able to write down. Not just that, one can now do something better. One can come in with 2 sources, right? I mean, I can use it's a 4-port device. I can always use 2 for input and 2 for output. And I can use this device and ask, oh, if I change if I change the phase between these 2 sources, S1 and S2, can I mold the flow of light? So you see that when the phase is 0 for the omega 1, and I think here the rod is at 45 degrees. Omega 1, you will start getting light going through only down. There is little transmission to the right. Similarly, for the other mode, for the source phase difference being pi, and can basically, and if I use any intermediate phases, I can basically change the thing. So here is a summary of this multiple source thing. I can put in 2 sources, and by varying the phase difference between them, get basically the required amount of light in either of the output channels, either the one which is going to the right or going down, and they are symmetric at theta equal to 45, obviously, given the symmetry of the problem, and theta equal to 75, obviously they are asymmetric. And you see, what is very nice about this is, you see these little circles and little triangles. So these little triangles and circles are our analytical calculation arising out of the superposition that we wrote down. And these other calculations are the full-fledged numerical finite difference time domain FTDD calculations, which gives you the peak. So I'm looking at the peak of the spectrum, and they match beautifully for these. So indeed, what we are proposing as a superposition is indeed governing this whole business. So essentially, something which are nice and intriguing to me, which I like, is that you see the mode rotation is happening because of this little rod. This is just to take stock of the situation, and probably I will take another 10-15 minutes. I'm probably well in time. So the mode rotation does happen. Not just that, orthogonality seems to be maintained. That is, moment I have where one of the modes aligns, the other mode spontaneously, please note the word spontaneously, aligns orthogonal to it. The other mode is, so, every time we get degenerate states in quantum mechanics, we teach students, you should always orthogonalize them. But this happens naturally. You put in a perturbation, and the system really loves orthogonality between the 2 modes. It is not something that we enforce. It seems to happen spontaneously. And then one can see that something other important thing which I want to just show you here, probably not visible, but yeah, maybe here in this view graph, you will see that if you look at the central region, you will see there is the dipole mode is there. It's of course little, because the rod is at a different, maybe 75 degrees here, I don't recall, because the rod is at a funny angle, it is not very symmetric. You see there is a null plane. There's a region which is perpendicular to the orientation of the dipole, which is a null plane. If you keep one of these waveguides along the null plane, zero light gets coupled. Okay, that's a very important lesson that we learned, which I forgot to emphasize. So waveguide coupling is negligible along the null planes of the mode. So you rotate the plane such a way that if you don't want any light to go through a particular output port, you simply make sure that you place the rod in such a way that the null planes of the rotated modes lies along that particular waveguide, and you would have negligible coupling into that waveguide. Okay, that's a very simple thumb rule that one can talk about. And this is the second part, which is enforcing strong perturbations. Now, if you put in a one rod, it's actually a very small rod. If you put in more rods, what happens? So you see that again, you are asking, essentially one is asking, how strongly are you breaking the symmetry? Is it a weak breaking of the symmetry or really strong? And what are the consequences? So I just dwell upon this just a little bit for next 10 minutes. There's a lot of pictures, no equations, but then we are looking at. So I'm looking at hexagonal symmetry. Please see that now the arrangement of the rods is very different. It is every rod is surrounded by 6 of the smaller rods, right? Every rod is surrounded by 6. Again, I do the same thing, take the central rod and increase its size. And again, I introduce this perturbation rod. So this is my hexagonal lattice. In this, I can retain the original 6. So now the symmetry governing is C4b Symmetry. And you can work out the details. And you see, I want to still maintain that symmetry. So I remove these rods along these 3 directions. So what you get is a 6 input output port device. And does the same thing happen? And the answer is yes, precisely the same thing. Just like the way we have to simply write it in a more complex and slightly more involved, mathematically involved looking fashion. But the game is exactly the same. For example, I'll just show you something. This is, for example, the unperturbed hexagonal cavity. I'm coming in with and exciting the dipole mode. So I come in with light, little light, 0.1%, 0.1%, or basically, sorry, 10% goes into these 4 regions, 60% goes here. So that is the way basically the light distributes itself when you come in from, this for the unperturbed hexagonal cavity. Now imagine that I put the rod at 120 degrees. So I put the rod along this direction, by the way. Now suddenly you see that I have shut off the propagation in various modes, and what I get is basically, about 7% here, and that's about it, right? Whereas for the other mode, again the rod is 120, so this is governed by a dipole mode which is aligned along that direction, and this is a direction which is perpendicular to it. So here you see, 50% light goes here, and 30% is basically going up and down. I have switched off the light going in the other channel. So you see, it gives you tremendous amount of control in terms of that. Now, why only look at a dipole mode? Let's imagine that I excite a quadrupole mode. Now you can clearly see that the modal structure is different at the center. And then again, you can play around with the same thing. You can, with the quadrupole mode, you'll have different numbers. So depending on which mode you are accessing, whether dipole, quadrupole, or for that matter, you can go even step ahead and maybe look at even a hexapole mode. Oh, sorry, so this is still quadrupole. Let me just tell you about this quadrupole mode. So this is how the quadrupole mode looks like, right? You can clearly, it's a quadrupole. Now what I do is, either I can take a single rod and twirl it around, that indeed we can do, or I can do worse, which is to now enforce a stronger perturbation, right? So I put 4 rods. These 4 rods are not oriented along the 30, 60, 120 degree direction of the hexagonal lattice. This was oriented maybe 15 degrees from the, so it is different orientation, right? It breaks the symmetry. So the overall there is a 6b symmetry, whereas locally I am now enforcing a 6-4b kind of a thing only locally, right? Now you see what happens is, now I am able to rotate this quadrupole, the quadrupole mode and the quadrupole alignment of the 4 rods matches. So what you get is a rotated quadrupole mode, and this is the mode which is aligned along the rod. This is the mode aligned perpendicular to the rod. Exactly the same things are happening. I'm able to generate 2 orthogonal modes. Not just that, wherever I had peaks now, they are now very nice null planes which are clearly visible. And with the perturbation of the 4 rods, one can again rotate this, and you see that this, because both the symmetries, quadrupole symmetry and the quadrupole, and the inclusion of the 4 rods also has a quadrupolar symmetry. Both of them match, hence we can rotate it. Now let us try and look at the hexapole mode. So this is the next slide. Probably you didn't realize it's the next slide, but now this is a hexapole mode. So this is just the central region, and you can clearly see these are now 2 different modes. By the way, these 2 modes are non-degenerate to begin with. They are not degenerate. Right? We'll have to look for different parameters it doesn't really happen. But now what I've done is, to this hexapole mode, I tried to put in a quadrupolar, the same arrangement of 4 rods with the quadrupolar symmetry, or symmetry which has got 90 degrees inbuilt in it. So this squarish symmetry, when you enforce it, you see these modes are indeed hexapolar, but they get heavily modified, and they start mimicking the symmetry which is enforced by this quadrupolar arrangement of the perturbation. So this perturbation is no longer weak. It is a strong perturbation, and you see that now these hexapole modes are indeed, now these 2 are orthogonal, but you see, but clearly they are not, they don't have the circular symmetry that we are very nicely looking for hexapole. It has got a squarish symmetry arising out of that. So you see that one can basically, so in conclusion, I have come to the end. What we have proposed is a simple and sort of a new, we believe, a new control paradigm. It is, people have seen, by the way, mode rotations in waveguides by introducing, if there are any defects in the crystal and in this photonic crystal fibers and so on, people have seen. But really, people haven't pinned down on the mathematical structure. That is precisely what we are doing. Of course, not in the waveguides, but we are doing it for the 2D crystal. I'm sure this can easily be extended to waveguides. And we believe it is a reasonably elegant description of the mathematical structure of the superposition. And once you know the mathematical structure, you can actually play with it. So one has done superposition, you can play around with the spatial orientation, bandwidths, one can play around with frequencies, transmission levels, and so on and so forth. And one can basically implement this in multi-port, multifunctional beam splitters, for example. Typically, you have a beam splitter that is a 4-port device. Maybe now you can think of a multi-port, multifunctional beam splitter where you can basically control. Then you can have multi-port band filters. You can design the quality factors and operating frequencies. I want to add just one more little thing. And actually there has been, and this is something that I should have mentioned early on. So there is always a huge problem now related to, how do you make this small rod in a controllable manner? That is going to be a challenge for the poor material scientists. But then optics people are very cruel. They always find a way out of it. So what you can do is you can take a femtosecond laser, right, and shine an extremely small, rather spatially small, localized field, that is a sharp, a localized field into this cavity, and basically, change the local refractive index. Okay, now we are talking about something called, if some of you are familiar with, intensity dependent refractive index. So this is something called, Kerr effect, to get some technical word. But then basically one can create a localized change in the refractive index, which is governed by the location of the beam that you're putting in. So imagine holding a femtosecond laser on top of this 2D structure, and moving around that little beam will actually create this appropriate refractive index defect, which is localized at different regions in a dynamic fashion. So we believe that this control paradigm can be implemented dynamically using the nonlinear light atom material interaction, and one can probably do this in a dynamic fashion and make it more useful in terms of control. So my apologies that actually these are both under review. the papers that I talked about. The first paper deals with most of the effects of the square lattice. The second one, which is probably coming in the Asian Journal of Physics, deals with the stuff with the hexagonal part. And all of this work has been done in collaboration with Gagandeep Kaur, who is probably also in the audience. She is a PhD student in the Center for Lasers and Photonics. And you can feel free to contact her or me in case you have more doubts in terms of email IDs, right? But of course, I will take doubts now if Aditya permits. Thank you.
Thanks, Professor Wanare. And now the talk is open for discussion. So if you have a question, you can write a name or the question in the chat box and we'll take one by one. Yeah, Shivram.
Hi, Harshad. Thank you for the nice talk.
Hi, Shiva.
Hi. So I had a sort of elementary question. So you talked about weak and strong perturbation. Correct. So what scales this perturbation strength? Which inherent parameter in the system?
Yeah. So yeah. Probably I did not emphasize that enough. My fault. Actually, this is the optical depth of the perturbation rod. Right. Okay. So see what when I choose a larger rod, right? I am basically within the band gap. I'm actually bringing down. I'm bringing down defect states within the rod, within the band gap, right? But I make this perturbation smaller and smaller, I don't really bring defect states into the band gap. All that I do is modify their energetics a little bit. So that bringing out extra states within the band gap or not bringing them is actually our measure of weak and strong. And actually we have seen extremely weak works. It works more beautifully because everything is linear in that case. So we would like to, because it's a probe and because it would be dynamically tunable, we are hoping that people will use it in the linear regime because then everything is very, very crystal clear.
Okay. I get that.
Yeah.
Maybe just a related question.
Sure.
So is there any difference between having an amplitude defect and a phase defect, if you wish? That the impurity modifies more.
Actually, let me be very clear. We have only introduced phase defects because we are looking at non-lossy medium. So all of these rods, I forget again, sorry about this. None of these rods are absorbing, right? But all that it will do is basically, it will keep taking away energy from your system. But there is nothing that stops it from. Imagine I come in with a metal, well below the plasma frequency, so that the penetration and loss is very small. Will I do the same thing? And answer is yes. Okay. Even that will do the same thing. I just said I don't want to, because I'm writing superpositions and something nice quantum mechanical, I want to avoid losses. And by the way, photonic structures, as you know very well, they are reasonably loss-free. They are really loss-free. So there is no harm in, so we have introduced in our study at the moment is only phase-like, if you like, loss-free inhomogeneities. Yes, thank you.
Yeah, thank you, Harsha. More on email, thanks.
Yeah, sure. Please, feel free. Yeah.
Thank you.
There's a question from Dhanoj.
Yeah, please.
Yes, thank you, Professor, for a very nice talk. I just wanted to know, is there any experimental theoretical ideas, if someone is doing that? Experimental stuff
actually, I would if you can do the experiment, I will start bugging you. So anybody who can do the experiment is most welcome to. We'll make your life miserable, but we are looking for partners who will implement it. We are talking to a few people, and it seems like doable. So experiments are most welcome to pursue this. We'll be very happy.
It's very nice. Thank you.
Have I? So I can only say welcome. Yeah. So please.
Thanks.
I would like to ask one thing, and I'm not sure if it will make sense or not.
Yeah.
But so the rod, the perturbing rod, right? So of course there should be some effect of its distance from your central rod, right?
Correct.
So the angle makes the rotation.
Yeah.
And now, I mean, the idea is what will get affected most? The angle of rotation or the transmission if you change the distance between.
Yeah. So I'll come to that. Let me just sorry. Let me just come to that part and I will show what I really mean. So you see, what matters is terrible. I am terrible at managing this. Please bear with me. I wanted to show you a formula which will probably, yes. Yeah. So if you look at your right corner, so you see there is a optical depth. Right. So this characterizes the perturbation rod, its radius and its refractive index. Right. Now you see the rest of these things. So that is this parameter which I can fully control. Whereas the value of it, its value, its radial distance from the center governs this prefactor. So once you fix the distance, for example, and the optical depth, you have fixed this prefactor. Then if you maintain the distance and simply rotate, then you are changing only this cosine theta. That's it. Right. That is precisely what one is saying. And indeed, what we do is we work out what this prefactor is numerically, and then and actually in the paper there are tables that give you this various factors. Just by you put in one source, you look at the prefactor, and once you have figured out this prefactor, this would work for all kinds of superpositions, all kinds of theta locations, all kinds of multiple inputs, outputs, whatever. It will work for it's the same prefactor that governs everything. Right. In that sense, right? So yes, indeed, the prefactor determines, for example, the distance. The rho is the radial distance from the central rod. D is the optical depth, and this eta is giving you that asymmetry factor, which is about 3 to 5%. But that basically governs it. And one more thing, a small qualifier, it also changes, for example, the bandwidth of the coupling to the cavity. So these are the kind of things. Maybe there is something else which only Gagandeep can say.
Okay, thanks.
I only work under her. Yeah.
Okay. So I don't see any more questions here. Well, in that case, on behalf of the society, let me thank Professor Wanare once again for accepting our invitation and giving this very nice overview. And I thank all of you also for joining us. The next colloquium in this series will be by Professor Bhas Bapat from ISARP Pune, and it's scheduled for 21st of August, and we will share the details with you in due time. So thank you all.
Yeah. Thank you very much. Thank you very much. It's been a pleasure.
Thank you, Harsha.
Yeah.